Hello everyone, I am Pierre Peterlongo, the last guy of this list, and it's a great pleasure for me to be here today with you and to have the opportunity to present to you this work that is a work in progress in collaboration with all these people, and I'm going to talk about the indexation of large and numerous sequencing datasets. And more precisely, I'm going to focus on this tool that we have called kmtricks. That is a tool for going from a set of reads, a set of read sets to kmers matrix. Of course, I would like to thank warmly organizers of this Biata to giving me the opportunity to present this work here today. A small word before to start about my research team. So my research team is called GeneScale. It's located in Rennes, which is a great city in Brittany, and Brittany is a great region in France. And we are working on the development and the implementations of algorithms for analyzing sequencing data. So classical stuffs like assembly, scaffolding, detections of variants, and their genotyping. We have proposed several tools for comparing the metagenomes. And we also developed some libraries or data structures. So for instance, Dominique Lavenier presented in Biata also 2 years ago the GATB library. And today I'm going to focus on the indexing purposes. Okay, let's start with a small motivation on why we would like to be able to index large and numerous sequencing datasets. Well, this is really simple actually. I'm sure you use daily some search engines on the internet. So for instance, here I've searched for Biata 2020. But can you imagine what would be the internet if we would not have those search engines? I would say not useless, but almost useless. We will not be able to access information that is stored on the internet. Well, this is precisely the case today with genomic data. So for instance, if you have a sequence of interest here, I don't know, a gene or, well, anything, there is no way to query the vast amount of sequencing data we have available today or assembled genomes we have available today with your request of interest. So for instance, here, if you try this on Google, or here it was on Quant, but if you try to find this sequence, there are no results because we are not able to dig into the databases containing those sequences. And this is a pity actually, because there are so many biological questions that we would be able to answer if we could query those genomic sequences. So I'm not going to present this into the details, but there have been some very recent studies in which at a smaller scale, they have been able to index some datasets, and they've shown some results thanks to this approach in many different biological studies. So for instance, with transcriptomics, analyzing genome dynamics, also this very important question about microbial genomics and applications in human health. So the key idea here is to say that with the access of the whole information we have available today, if we would be able to search in this data, this would open so many biological studies, and we would really be able to access the richness of those data. And maybe this would be the end of this classical scheme we know today. First, here, it's not written in my slide, but you write some grants, you have some money, you are able to sequence your data, And then you do your analysis on the data. So for instance, with assembly or mapping, you publish your paper, for instance, and then you put the data in some drawers, you close the drawer, and you cannot open them. Well, you can open them whenever you want, but usually those drawers, they close because we are not able to search in them. Okay, you are not able to if you have a sequence of interest, you are not able to know in which drawer the sequence of interest occurs. And this is exactly what we would like to end. And this would enable to combine the analysis of many datasets. So this would be the end of the analysis of your dataset alone, but you would be able to analyze your data with respect to whatever the information we have already acquired. And this is really challenging. So I'm going to talk a bit about the Tarosian project. We will see what it is just afterwards. So it's kind of small scale, big project. We have here 250 billion metagenomic reads, but we can also, of course, talk about human projects. For instance, the 100,000 genome projects that contains 19 petabytes of compressed FASTQ sequences. And of course, the ultimate goal would be to be able to index and to be able to query the whole EBI European Nucleotide Archive reads. And here we have approximately today 600 petabytes of data, and it evolves very quickly. And once again, this is really challenging because if we look, for instance, to the indexed web, we can estimate that it represents approximately 100 petabytes of data. And as you can see, this is already much less than what would be to be indexed in the whole nucleotide archive. So this is really challenging. And this is a small spoiler. This talk is not going to answer directly this challenge. It's one step to go to the answer, unfortunately. We are not starting from scratch. There are some solutions. And here I'm going to talk a little bit more about Tarosian, as I told you, just because this is a great story and because there is an example of the usage of the ability of querying those data. So Tara, this is this amazing boat that went all around the world in different expeditions, and it sampled some seawater. So we have like thousands of seawater samples that have been sequenced and somehow analyzed. And what they have done here, people in charge of this data were able to assemble from the meta-transcriptomic data, they were able to assemble genes and to propose this server, for which you have the address here, where you can query some sequences. So this is a small movie with an example of the query you can do. So you query your sequence of interest, and when you obtain results a few seconds later, you have a lot of information of interest. So for instance, you can see the value of the answers, where your query occurs among the oceans, at which depth, for which temperature, and you have the pronouns of the datasets you have found. So this is the kind of global information you can get from those indexing strategies. And so this is starting, this is great, but for instance, in the case of this specific server, this is limited to a small amount of the data. So here this is only genes, assembled genes from the whole meta-transcriptomic data. This uses some classical tools like Blast Diamond or Kmer. And so this is interesting, but we must do better. We must scale to larger scale. And to go further, what we do usually, what everybody does, is to go from the query of sequences, so to go from the alignment of sequences with quadratic complexity to the usage of K-mers. So to make it simple, K-mers are words of length K. So this is the definition. One K-mer is a word of length K. And what we would like to do is the following. So you have, for instance, a large bench of data. So for instance, assembled genomes, or as written here, some read sets. And you have one or several query sequences. And for each of those sequences, you would like to know a binary answer, at least to know in which of those datasets the query belongs. Where this query occurs. And instead of, as I said, instead of aligning the sequences, we go to kmers. So you convert your query sequence into overlapping set of words of length K, kmers, with K defined, for instance, equals to 20 to 30 nucleotides. And you transform also your index, well, your datasets into their set of kmers. So you index their kmers. And once you have done, what you do is to query the kmers of the input sequence. And for each of those kmers, you are able to know in which dataset they occurs. And you have some thresholds. So for instance, here we have a threshold of 4, and we say if we have at least 4 kmers that occur in D1, we would say that the query sequence occurs in D1. And you're able, with this kind of approach, to know, to answer, okay, your query sequence occurs in the first dataset, it does not occur in the second, it occurs in the third one, and so on. But for doing this, what we need is there an index represented here as a black box, and this index must be able to answer the very simple question: does this kmer, so for instance here I took a kmer of length 10, does this 10-mer occur in dataset 1, does it occur in dataset 2, and so on, sorry. So where does this K-mer occur? This answer must be very fast. So for instance, in constant time with very small answer time. And once you have this, the main idea is to look one by one to all the K-mers and to know for each of those K-mers where they occur in all the datasets with this black box. And so I'm not going to present to you detailed state of the art of those existing indexes, but there have been a lot of exciting researches around those indexes those last few days. And there is currently an excellent review that is available on bioRxiv made by Camille Marché and her collaborators. So I really invite you to have a look to this review if you're interested to all existing solutions. And I just took one table from this review. This table represents some results on a very common dataset composed of almost 2060 read sets, almost 8,000 billion base pairs in this read set. So it's big, but it enables to make some benches. And most of the papers of the studies that propose new indexes use this dataset to make it, and it's human RNA-seq from different tissues. So on this table, you can see some metrics to assess the ability of different tools to create the indexes. So it's only the index creation step here, not the query time, but only the index creation time. And we're going to focus in this talk on the one of the most efficient one, which is called HowDSBT, because this is the fastest to create the index with a small amount of RAM memory. Sorry, a small amount of disk. Also a small amount of RAM memory. It's not written here, but it's really acceptable. And one of the most important thing is that the final index is one of the smallest. So for instance, for this data set, which is already quite big, the final index size is 15 gigabytes. And the motivation for this talk and for everything, for instance, here, is if we project the indexation time we had here on this data set, if we would like to index the whole Autorocean project with HowDSBT, it would need 100 to 200 days. So we would like to propose better solutions. Okay, so I hope everything is going well up to now. And before to go further, I need to spend a few minutes on reminding what is a Bloom filter. I'm conscious that maybe most of you know what it is, but I really need to be sure of this because all the rest is based on Bloom filter. So I need to make a very quick reminder. So Bloom filter is certainly the most efficient data structure available today, existing today, to store a set of elements, to be able to index a set of elements. And it's really simple. It's composed of a simple vector of bits of 0 and 1s. The idea is when you want to index an element, for example, x here, you compute a hash value with a hash function, and you put a 1 into the address that is pointed by this hash value. So you put here 1 for the element x, and you do this for all the elements. So here for the 3 elements, you put a 1 to the 3 corresponding addresses. Once you have done the indexation, when you have done this step, when you query an element, for instance, W here, you also compute with the same hash function, this hash value, and if you find a 0, this means no, your element was not indexed. If you query one of the elements that you had indexed, you will find a 1, so you can answer yes, your element was indexed in the data structure. But you have some false positives because, for instance, you can query an element that was not indexed, but because of collisions of the hash function, you find the same hash values and something that was indeed indexed, but this is a false positive. So you have a false positive rate that depends on the size allocated for the bit vector, and that also depends on the number of hash functions that have been used, but this is not presented here. But anyway, in terms of space, this is really efficient, and we can deal with a small false positive rate for this kind of queries. In practice, if we come back to our problem, what we do, if you only have one data set, for instance, here, you have created its Bloom filter, and when you make a query, you query all the kmers, and so you can know which kmer were present in your dataset. If you have several datasets, you create one Bloom filter per dataset, and when you make the query, you can query if the dataset have if the Bloom filters have the same length. If the datasets have the same length, I don't touch this anymore. The key idea is that you compute one hash value per kmer, and you can read directly one line of all those Bloom filters. So you can compute only one hash value for each kmer and find directly in which dataset those kmer occurs. This is a simple idea and that was efficiently implemented in an important tool called Big-C that was published 1 year ago by Bradley and All. And this is one of the efficient way to index a large set of datasets. So the idea is clever, it works well, but we can do better, and this is what is proposed. If you want to, well, this is what is proposed in a data structure called SBT for sequence Bloom trees, where you organize your Bloom filter in a tree. So the idea is to put the more similar Bloom filters in close leaves in the tree. And for each internal node, you store the union of the child nodes. So this is the same thing as if you had indexed a concatenation of the two datasets. If you look to this internal node, for instance, and so if you have a 1 here, you know that the kmer, well, the hash value associated to this kmer occurs in at least one of the Bloom filters in the subtree. And so if you find a 0 somewhere, you know that the kmer is absent. And hence, in this case, it's not necessary to go deeper in the tree because you know that you're not going to find your kmer here, so you can prune the query earlier. Our DSBT is an improvement of this idea. So we also, well, look, for instance, to the blue kmer. This blue kmer occurs in all the Bloom filters that are stored in the leaves. And so you can make this information available in internal nodes and in the root of the tree. So you can say, okay, I know that this thing occurs everywhere in my experiments. In the same idea, you can say that the red kmer here occurs nowhere, in no experiments. And so we would like also to be able to store this earlier in the tree to be able to stop the search in the subtrees. And this is this key idea, so I'm going to explain this to you in a few seconds or minutes. This is not really the topic of my talk, but this is a very clever idea, so don't look to all those formulas. I'll try to explain this to you with this picture. Let's look to the root of the tree. And in the HowDSBT data structure, for each node, you have 2 bit vectors. One that says to you if a kmer is determined. So determined means that in all the subtree, this kmer have the same value. And if it is determined, so if you have a 1 here, it says to you how it is determined. So in this case, this kmer has the same value everywhere, and its value is 1. So there is no need to go in the subtree because you know that this kmer is present everywhere. In the same idea, this second kmer is determined, it's the same value everywhere, and its value is 0. So you know that it's absent everywhere. Those 2 kmer are not determined because they have different values in the 2 subtrees. And for instance, if we go into this part of the tree, so we do not store anything else for those 2 first kmers because they were already determined higher in the tree. And for the third kmer, you know that in all the subtree, its value is determined, it is 0, and so on and so forth. It's a bit counterintuitive because you can think that we use here 2 bit vectors instead of 1 for each node, and so we should use more memory, but actually we store only the determined, not the determined, but the active bits. So, for instance, those bits are called inactive because we do not need them anymore. And so we do not redundantly store useless bits. And as this is very common in this kind of approaches, once we remove inactive bits, we compress the remaining vectors using RR. All right, so this was AuDSBT, the core concept of AuDSBT, but now we go a step back and we look the overview of the AuD construction. So how AuD is constructed: you take your input read sets, you counter kmers because we would like to remove low abundant kmers. So the first step of all the methods based on kmers consists in counting the kmers. So here, for instance, kmers that are present only once are removed. This is done with jellyfish in AuDSBT. From all those counted kmers, you compute one Bloom filter per read set. You compute the tree topology by clustering those Bloom filters, and then you construct the AuD structure. And now, after almost half an hour of talk, I come to the work we would like to propose today. This work is called kmtricks for K-mer matrix. And here, I took the motivation of improving the whole AuDSBT pipeline, but this is a kind of general purpose approach, kmtricks, that is able to go from a bench of read sets and to go the most efficiently as possible to a set of Bloom filters, or also a step of counted kmers matrix. But here we show the result in the framework of AuDSBT. A small warning, so this is still an ongoing work, and we hope that we think that it's going to evolve quickly in the next few months, and we have a lot of ideas to make it better, but you are welcome if you want to get involved or use the tool, anything. This is really open and friendly. And we propose some improvements that I'm going to show in more detail right now. So here in gray, this is what we did not change at all in the whole pipeline of AuDSBT. So let's focus on this part. First thing we have done is to go from jellyfish to DST, which is a bit more efficient than jellyfish. So we have the same result. We have the counted kmers after this step. We would like to take the opportunity to have all those datasets represented together, to have a more clever way to get rid of low abundant kmers. So the key idea is a bit more biological here. We think that, for instance, a kmer that is said weak or rare, well, a kmer that we would have removed with the previous approach, if this rare kmer occurs somewhere else, where, rare or not, well, if this kmer occurs somewhere else, maybe this is not a sequence due to a sequencing error. Maybe this is a very low abundant species in metagenomes, for instance, or very low abundance strains in any microbial gut, for instance. So what we do here, well, this is an option, but what we can do is to save it. We do not consider it as a sequencing error because this is redundant among read sets. Okay, so this is the second proposed improvement. The most, let's say, algorithmic idea we propose is the following. What we want at the end of this pipeline is a set of Bloom filters. So instead of counting kmers, maybe we can directly count their hash values, given the hash function. So if we directly count their hash values, what we obtained is almost here some Bloom filters. So what we do is during this step, we store the hash values with their counts. How do we do that? Just a little focus on this part. So this is parallelized. For each reset, so here on this slide, I focus on the first reset. We divide, thanks to minimizers, the reset into several partitions. So here I represented 2 partitions, but we have hundreds of partitions. For each partition, thanks to the super K-matrix, we compute the kmers and we directly output their hash values, and we sort those hash values and we count the number of occurrences of each hash value. So once again, I'm not going to go far into the details because we here have reused some known tricks from TMC to use super kmers, to use minimizers for the computation of these abundances very efficiently. But the key idea is that we directly store those hash values. This part is written on disk. We do this for all the sets. So we have those counted hash values for all the partitions of all the read sets. And from all those partitions, we merge them. We add some empty lines for the hash values that were not encountered before. We can do the trick where we save the rare shared kmers. So the kmers I was talking before, we still remove kmers that are rare in only one dataset. Here I've written that it's not stored, so all those steps are done in memory. We go from counted to binary values. So here we have some sub hash, some sub Bloom filters, sorry. And one important trick that I have not mentioned before is that when we create the partitions, we do this in a way that the hash values, the smaller hash values, occur in the smallest hash, in the smallest partitions, and bigger hash values occur in bigger partitions, and so on. So what we have to do once we have this, it's only a concatenation of all the sub-Bloom filters. Once we have done this step, just to mention it, once we have done this, we have exactly what is needed by Bixby to compute its data structure. But we still have one step beyond to plug our Gmer-traits to our GSBT. Is here, once we have done this, each Bloom filter is available in one column, and what we need here is one row by Bloom filter, so we need to transpose the matrix, and once this is done, we have exactly one Bloom filter per line, so we can directly feed the final the construction step with those Bloom filters. And we do this transposition using SSE instructions, and this is something also that may be interesting as a standalone tool. All right, so I think I have finished with the presentation of kmtricks that goes from the read sets up to the Bloom filters in the most efficient way that we had in mind today. So, as I said, this is still in progress. There are still, we have a lot of ideas. but I guess today this is the most efficient way to perform all those steps. Let's have a look to the results. So maybe I could have removed the S here of result, this one, because this is really preliminary. Today, when I record this video, I have only this one slide to be presented to you, but I hope in the question and answer session I will have more results to be presented. But just have a look to this one. So here I took again the classical RNA-seq datasets I've been talking about a bit earlier. I didn't took the whole almost 2,600 datasets. I just took the 101st of them. This represents approximately 800 million reads. It's a small dataset with 44 gigabytes of compressed FASTA files. But just as comparisons, if you take the creation step of the Bloom filters from Audi, it takes 2 hours and a half with a small amount of memory, so this is really affordable. And peak disk usage is 55 gigabytes. 55 gigabytes. This is more than what is presented in the table I have shown to you earlier, but this is because here we kept all kmers occurring at least twice, while in the original publication there are some thresholds per dataset with very high threshold for some dataset threshold equal to 50, for instance. So here we took a lot more kmers. As a comparison, kmtricks here took a bit more than 1 hour, so it's more than twice as fast as Audi MacBF steps. The maximal memory is much lower, but this is not really important because, as I said, this is really acceptable. There are no steps where you put all your data into RAM memory, so it will not be a problem. Sorry, I don't find the word. It will not be a problem to. We won't have internal memory problems for indexing data. The disk usage here is twice as big as Audi. But in our current implementation, we compute all the counted super kmers at the same time. So we store a lot of information on this, but in the near future, maybe for next week, if I'm really optimistic, we can have another way to organize computations, and we can have a peak disk usage limited to the bigger dataset, so a very small disk usage. If you look to the distribution of steps by kmtricks, what we can see is that the creation of super kmers, so the first step, the count of those super kmers take almost all the time. So the count is much more than half the computation time. And this is where we should focus, all of us in the future if we want to scale to huge datasets. So the merging time where you put all the Bloom filters together is quite fast, and the transposition of the final matrix with the SSE instructions is also very fast, so less than 3 minutes here. Okay, so this is actually my result side. I would have expected to present much more, but I hope that in the near future we'll have much more results to present to you. Okay, so this is not my take-home message because we are home, so this is a stay-home message. In a nutshell, so the kmtrick tool is available on this GitHub together with a modified version of Howdy SBT because we changed the hash function, so we just had to adapt this step of Howdy SBT. So you will find also a way to install this modified version of Howdy SBT. And so in a nutshell, what kmtricks does is from the input set of sequencing datasets, we propose a classical K-mer counting approach. And well, my key message on this slide is the following. We have proposed kmtricks with the results we have just seen before, but all the tools have been thought to be used independently from each other. They have been well implemented by Theo Lehmann. We are going to see him in a few slides. As independent libraries, so you can use them for any computation step in your development if you're interested. So there is this classical step of K-mer counting using super kmers. You can output plain kmers with their abundance or only presence absences as hash values or Bloom filters also. We are able to propose the full K-mer matrix, once again with only their binary values or their abundances. This K-mer matrix can also be streamed line by line instead of storing it directly and fully on the disk if you do not have a space. As I said, we propose this matrix transposition step that could be also really interesting as a standalone tool. So you can take any matrix. So the only restriction is the fact that the matrix must be number of lines and columns must be multiple each of 8. So, well, this is not that important, but think about that if you want to use this module. And we really think that this kmtricks tool has a general purpose usages like the indexation as we saw here today, but if you want to do some genome-wide analysis studies, phylogeny studies, also metagenomics if you want to compare large bench of data sets, and so on. Of course, everything has been done in parallel as much as possible. So this is, we use as much as possible the number of available cores and threads. We have proposed a faster Howdy SBT construction, so we are quite happy with this result because nowadays, as far as I know, Howdy SBT is the fastest tool to construct the indexes for large bench of read sets. So divided by 2, the construction time is already something really interesting. And as I said, we're able to keep those rare shared kmers. In the near future, about kmtricks. So as I said, we would like to be able to improve performances. First, one of the most important things to do is to limit as much as possible the disk usage. This will be done if it's not done already. There are also some interesting questions that are quite general also, but how to use exactly the good number of partitions that takes the best of the available computation facilities you have. This is not a very simple question actually, and this is also a very general question when you want to use as nice as possible the computational resources you have. Now, if we have a look to the combination of kmtricks plus our GSBT, we also have some questions that we are going to dig. Today, we construct one big tree for all the computing partitions, and maybe it's more interesting to construct one tree per partition or one tree per subset of partitions, and to manipulate smaller smaller data structures. Maybe it will provide some important improvements. From a more biological point of view, we need to assess the effect of indexing rare shared kmers. Are we going to save interesting sequences, or are we going to store some erroneous kmers? Well, of course, we are going to do the two, but we have to assess precisely what is the impact of this approach. And of course, one of the key limitations today is the dynamicity of this data structure in particular, because it's not that simple to add a new data set. But in practice, if we look only to the algorithmic point of view, this is not that difficult to add new datasets or new benches of datasets, because as we saw on the results, once we have the Bloom filters, the last steps of constructing the tree of the final ODSBT data structure is not that long. So when you add some datasets, maybe we can afford to recompute the whole tree, or we can construct some different trees and merge them afterwards. So there are some ideas to be able to be dynamic. But of course, with rare shared kmers, this is not easy, because we have to recompute the Bloom filters if we want to handle those rare shared kmers. So we have some questions here to answer. And finally, my last message is the following. The indexation problem is not over, and it's not over by far. So if we want to, if we're thinking about the time that would be needed with those existing approaches to index, for instance, the water oceans project, so this is feasible, it will need 50 to 100 days, and this is affordable in our current clusters in terms of disk space and RAM, internal memory usage. But now, if you look to the whole European nucleotide archive, maybe most of us will be dead when this is over, because it would need 1,000 years with those current approaches to index this whole data set. So we still need dramatic improvements. This is good to divide the indexation time by 2, but we would need to divide it by 1,000 if we like to really be able to access the dream of being able to query those sequences. And I was thinking maybe it's not in the political ideas of SRA, for instance, but maybe we could impose, because the idea is that almost everybody, once you have your data set available, you count the kmers. You count the kmers when you do the assembly of your data. So almost almost all of us have counted the kmers of its data sets. And as we saw in the previous results, this is the most time-consuming task of the indexation. So maybe we could impose to people, when they store the data on public datasets, maybe we could ask them also to store their counted kmers. If everybody does it, if everybody does this, we would have directly those counted kmers available, and we could make the queries on those counted kmers. We could construct very efficiently some indexes to be able to query those datasets. So this is an idea, maybe a bit counterintuitive because we need some space to store those kmers, but this would evolve. This would enable us to make those queries. Well, that's it. I would really like to thank people we are working with on this project, and in particular, I would like to thank Theo, who is a PhD student and who made most of the developments of the tools. And thank you very much for your attention, and I hope we have some nice question and answer session, and I also hope that you could be interested in working with us on this project. Thank you very much.